Hi Rockridge, it's Mrs. Brooker. We are in Algebra 2 and we are going through our new lesson on graphing absolute value equations and inequalities in two variables. Last class we addressed the algebra of absolute value equations and inequalities. Remember the less than, ands, and the greater than, ors, and the equalities having two answers. We're going to do a little bit of a warm-up on that material, which will flow right into today's unit on graphing. So let's take a look at this warm-up here. Remember, the first thing we always have to do when we are doing these absolute values is isolate the absolute value portion first. So we have a couple of steps to do that in here. So we need to subtract 2 from both sides first. And then we need to divide by -5. And remember, this whole time our absolute value bars remain in place. We still have this 5m minus 5 within the absolute value bars. Those don't leave. Also, we never ever distribute within the absolute value bars. They're in jail, nobody goes in, nobody goes out, okay? The only time you can break these out of jail is when you've finished the isolation step. Then you do your setup. You say 5m minus 5 equals 15. And 5m minus 5 equals 15's evil twin, -15. Now you solve each side. Add 5 to both sides, divide by 5, add 5 to both sides, divide by 5. Those two answers are the two solutions that make the original black equation work. Okay? Number 2, we have some isolation to do. We need to divide by the -7 first. And we have x plus 2, absolute value, equals -4. And remember, this is still within the absolute value jail. Now remember, whenever we have a negative, after our isolation steps are complete, if we have a negative over here, we likely have a special case of some kind. Today's special case is the absolute value of something can never equal a negative. So because no absolute value can equal negative, this has no solution. There's nothing you could possibly put in for x and then take the absolute value of it and have it equal a negative of any kind. So this one has no solution. And again, we usually look for that when we've got negatives after all the isolation steps are finished. So we're finished with that one. No extra work needed. Number 3, we have an isolation step to do. We divide by -2. And this guy is an inequality. So when I divide by the -2 for isolation, I have to flip the direction of this. So I've got the inequality is less than or equal to a -5. Now, once again, I have a negative over here, so I need to check for special cases. So let's think about this. Can I spit out, whatever I spit out of here is going to be a positive number. Can a positive number be less than or equal to a -5? No, it can't. Positive is never less than negative, right? That never happens on a number line. Anything less than the negative is going to be even more negative. So this too has no solution. Can't be less than or equal to a negative. So nothing I put in for x will cause this absolute value solution to work. Number 4, we have some isolation steps to do. The first one being subtract 9 from all sides. So let's subtract 9 here, and remember, everybody else stays the same as we're doing this subtraction. Absolute value bars stay in place. This -1 being multiplied out here stays in place. Alright, we've subtracted 9 from both sides. Now let's divide by a -1 to isolate this absolute value. When we divide by a negative, we have to flip the direction of this. And now we have the absolute value of something is greater than or equal to an 8. Now remember back in this step, we were a little bit worried, right? We saw this negative over here and we're thinking, oh, maybe we have a special case. Don't make that determination about special case until you've made it all the way down to the completely isolated absolute value. Alright, we've got an absolute value isolated here, and we're ready to set up our two-step inequality here. Now we've got a greater than at this phase. We've got a greater than, so a greater than is an or. So that decision is made for me. 3 minus m is greater than or equal to 8, or 3 minus m is less than or equal to its evil twin, negative 8. Subtract 3 from both sides. Divide by negative 1 and flip the direction. Subtract 3 from both sides. Divide by negative 1 and flip the direction. So here's our algebra. We're saying m is less than or equal to a negative 5 or greater than an 11. We've got less than equal to the negative 5, so we're shading in this direction. And we've got greater than a positive 11, so we're scribbling in this direction. And that's exactly what we would expect from an or statement. Or statements should always have going off in two different directions. Let's take a look at number 5. First step is to subtract 11 from both sides. Absolute value bars stay in place. And we do not distribute this 1/2. Absolutely not. What do we do to get rid of that 1/2? Well, in order to get rid of it, we need to either divide by a half, or I like to think of it as multiplying by its reciprocal 2 over 1, which is the same thing. Dividing by a half, multiplied by the reciprocal, same thing. So that's how we get rid of that. 2 over 1 times a half, that goes away, so I'm left with just the absolute value of 4x minus 1. Is greater than, since we're not multiplying by a negative 2 to get rid of it, we're multiplying by a positive, we don't have to change the direction. 2 times 2 is 4 over here. Notice my absolute value stayed the entire time, and I never distributed, I never crossed the bars. Now I'm ready for the setup. What kind of setup do I need here? I have a greater than, or. Here's my setup. 4x minus 1 is greater than 4, or 4x minus 1 is less than the evil twin, negative 4. Add 1 to both sides. Divide by 4. Add 1 to both sides. Divide by 4. Sorry about that. X is less than negative 3/4. And again, we have an or statement. We have a negative 3/4 on the left, and we have a positive 5/4 on the right. We are open circles everywhere. If we are less than negative 3/4, we're headed this way. If we are greater than positive 5/4, we're headed that way, which matches what we would expect from an or statement, off in two different directions. Number 6. Let's divide by the negative 4 to isolate the absolute value. The absolute value bars come along for us. When we divide by the negative 4, we must flip the direction and make this a greater than negative 6. Now, we are isolated at this point, and we have a negative over here, so let's take a look at what we've got going on. Absolute value of something is greater than a negative. Is that okay? Absolute values are always positive, greater than a negative. Yeah, that's okay. In fact, that's always okay. Anything you put in here, in this absolute value, is going to be greater than a negative 6. All positive numbers are greater than negative 6. So since positive over here is always greater than a negative, let's do negative, that means all real numbers can make this a true statement. You can put anything in for x, and this will be a true statement. So you can say all real numbers, or you can do the shorthand, either way, to indicate that anything can be put in here to make this a true statement. And we shade the entire number line. Remember, we're always making these determinations at the isolated absolute value step. The determination of whether it's an and or an or, the determination of whether we've got an all real numbers or a no solution situation. That's always happening after the isolation is complete. All right? All right, that is a great segue into today's new lesson on graphing. If you recall, a graph of an absolute function is always a V-shape. Remember that? Every time we graphed an absolute value, it was a V-shape with a nice pointy vertex. It's also symmetric, and we'll talk a little bit more about its symmetry today. So keep in mind that it's always a V and it's always symmetric. Now the general form for an absolute value function, we've seen the HK format. The general form is very similar. It looks like this, A on the outside. Sometimes we might have a B in front of the X. We haven't seen that yet. We'll see that today. Sometimes we have a B in front of the X that's not a number 1. And then we have plus C in here, plus D. So that's the general form. That's the standard form of an absolute value function versus the HK format. We'll still make use of our HK skills today, though. All right, we're going to graph each of these by hand, and we're going to identify the vertex, or the HK starting point. So that was HK for us, just to remind ourselves. We're going to identify the axis of symmetry, or the line that cuts it perfectly in half. We say AOS for short. And the direction, we're going to tell whether it's up or if it's down. And what I mean by that is an upward-facing V or a downward-facing V. So let's identify all of that for these problems. Let's graph them first. Where is the vertex for number 1? Well, we know how to pull that off. If we see something like this, we pull that off as the HK, right? The H is 3, and the K is this invisible plus 0 on the outside. So a 3, 0 is the vertex for this. Which way is it facing? What direction is it? Well, out here there's an invisible positive 1. So since it's not negative, it's got to be facing up. And since it's an invisible positive 1, we know it goes up 1 over 1, up 1 over 1, and then in the other direction, up 1 over 1, up 1 over 1. If you don't know that straight off by hand, you can always do a table of values. You can graph it on your calculator and pull off a table of values. Or again, you can just memorize that out here as your quote-unquote slope. What is its axis of symmetry? What is the line that would cut this thing perfectly in half? It's this line right here. And what's the equation of that line right here? The equation of an axis of symmetry for an absolute value is always x equals something. X equals 0 in this case. The axis of symmetry is always a line of the form x equals some number. And you'll see that that number is always the h of our vertex, right? It's always the x value that goes right straight through the middle. Don't ever tell me the axis of symmetry is 0. Oh, and I wrote that wrong too, didn't I? It's not 0. It's the h, not the k. It's the h, not the k. The axis of symmetry is x equals 3. So don't ever tell me that the axis of symmetry is 3. You tell me the axis of symmetry is the line x equals 3. Okay? And that's always the h. It's always the h. All right, now let's look at number 2, which is a little bit different than what we've been seeing. This is not an equal sign here. This is a greater than sign. So let's see how that plays out. Let's pretend for a moment that it was an equal sign. How would we graph this? Well, right now we have an h of 0, basically, right? And a k of 4. So our vertex is 0, 4. 0, 1, 2, 3, 4. So this is our vertex right now, if this was just a plain old absolute value equation. If this was a plain old vacation, we would, if it was a plain old equation, we would look out here to see if we had a positive or negative or some number. We don't have anything, so we have basically an invisible positive 1. So we know it's an upward facing, and its slope is basically up 1 over 1, up 1 over 1, and back 1. And so basically this thing, if it were an equation, not a vacation, but an equation, that's what it would look like. But it's not an equation, it's an inequality. It's saying it is y's are greater than this graph. And what that means is y's are all above this graph. Y's are greater than this graph. But it also says they're greater than but not equal to this graph. So that means we need to get our little eraser and make this a dashed line to indicate that we get real close to this absolute value v, but never actually reach it. We're greater than, but not ever equal to this v. That's what greater than looks like. It's a shading above, but not equal to, not solid. In our last little step here, we can declare that our axis of symmetry is the line x equals 0. X equals 0, the line that goes straight through the middle here, x equals 0. Let's look at number 3 and see what we have to work with. Again, let's pretend this is an equation for right now. What would we do to graph this? If this was an equation, we would pull the hk off and make a vertex at 3, 1. So at 1, 2, 3, 1 is our vertex. Then we take a look at direction. We look out here and see a negative, an invisible 1 here, so negative 1, so we know it's a downward facing direction and of a quote-unquote slope of down 1 over 1 for each little point here, okay? So if we were graphing an equation, we would graph it like this, but it's not an equation, right? It's an inequality. So what is this inequality saying? It's saying y's are less than this graph. Less than this graph means below this graph. Less than but not equal to means I have to take my eraser and make this a dashed line to indicate I never actually reach the line. So now I've got my graph. I am less than the graph but not equal to it. I'm shading down. I'm downward facing. The last question I have to answer is this axis of symmetry question. If you already figured this out, I just say x is equal to the h of the equation. If you want to visually check that out, you can go, oh, well, the line would go right here, and the equation of that vertical line is the line x equals positive 3. Okay. All right, let's take a look at 3 more of these and see how they can present themselves differently. We've still got an HK format that we're used to in this one. So we can grab the HK off. This would be a negative 4, 0 vertex. So back 1, 2, 3, 4, and not up or down. If you would like, you can immediately fill in the axis of symmetry. It's going to be the line x equal negative 4, because we know that without even drawing it, just from the algebra. Is it an upward facing or downward facing? Well, there's an invisible positive 1 here, so it's an upward facing, up 1 over 1 situation. So the answer here is upward facing. If this was an equation, we would draw a nice solid line through this and be done, but it's not an equation, it's an inequality. Y's are greater than, but not equal to. So if you don't want to do the eraser trick, you can just start off by doing dashed lines to begin with to show that we get close to this absolute value graph here, but never actually sit on this line. And we are greater than, so we're shading above. We're greater than, so we're shading above. Number 5, we have a little bit of a different situation here. We've got a vertex sitting at 4, 0. So we're good there. 1, 2, 3. There's 1, 2, 3. Yes, okay. Good there, 4, 0. And then our direction is up because this is a positive. It's up, but its up is a quote-unquote slope of 2 over 1. So instead of going up 1 over 1, we have to go up 2 over 1, up 2 back 1, up 2 over 1, and up 2 back 1. So it's a little bit skinnier. Our axis of symmetry is still going to be x equals 4, goes straight down the middle. We are less than but not equal to, so we can't do a solid line. We need a dashed line, or draw the solid line and then erase it to be dashed. So we have a dashed line, and we are less than this graph, so we actually need to shade everything below the graph. And if you don't want to spend too much ink or pencil lead, you're more than welcome to sort of just indicate here. As long as you're not showing that it's above here, I get the point. Everything less than here, but not equal to. Make sure you've got dashed and underneath, and you'll be good. Number 6. Number 6 is interesting. We have a couple of things going on here. We certainly would like to jump in here and grab this 4 as the h and this negative 3 as the k. We're actually not allowed to do that yet. You see here this number that's married to this x in here, or this b value from our original standard form. This is preventing us from grabbing negative 4 as the h. We can't grab that as the h until we factor out this 2. We need to pull this 2 out of here before we can grab the h for our hk starting point. Okay, you can never grab this if there's a number attached to here other than positive 1. So in order to do that, we need to factor out a 2. And by factoring out a 2, that basically means I need to divide this by 2 and divide this by 2 and see how that ends up for our inequality. So let's rewrite this. Let's say y is less than or equal to that 1/2 that was already sitting there times the 2 that I'm pulling out of the absolute value, leaving behind x minus 2 minus 3. Okay, that's our new absolute value inequality. And now that this x doesn't have anything attached to it, I now can pull my hk out. Not until then, though. So that's our last little special case of the day. What's our hk vertex? It is negative 2, negative 3. I'm sorry, it is positive 2, negative 3. X minus h. So positive 2, negative 3 is our hk. Positive 2, negative 1, 2, 3 is our hk. That's our starting point. Now, let's go see if this is upward facing or downward facing. What do we have out here? Well, we have a 1 over 2 times a 2 over 1, basically, right? 1 over 2 times 2 over 1. So this is essentially the number 1, and it's a positive 1. So our direction is up, and our quote-unquote slope is up 1 over 1. It's a positive 1 that's now sitting out in front of our absolute value. All right, so this is what that v would look like if it was an equation. Now, what do we have with this inequality? We have less than equal to. All right, neat. So, less than equal to, that means I can draw this as a solid line. I can draw this as a solid line because I do actually equal this, and I'm also less than this. So that's essentially what your graph looks like. It's not dashed this time. It's solid this time because I'm less than and equal to. What's our axis of symmetry? It's still the x equals 2. All right? Now, we have taken the algebra and gone to the graph for these last 6 graphs. Let's take the graph and build the algebra now. Let's look at what we have in number 7. Number 7, we have the graph of an absolute value equation, right? We have no shading, there's no dashed, it's just the equation. So we know that takes the form y equals maybe something out here, absolute value, some kind of x in here, right? This is the skeleton of what this graph's algebra looks like. Let's fill in that skeleton based on this hk starting point. What is the hk? It is 2, comma, negative 1, 2, 3, 4, negative 4. I highly recommend you write this starting point here as a reference before you build your equation down here. All right, if we have a 2 as our h, that means we say negative 2 in here. If we have a negative 4 for k, we put a negative 4 out here. Now this is an upward facing, so I know it's positive, some kind of positive thing out here. And to get from one point to another, I go up 1 over 1, up 1 over 1, up 1 over 1. Therefore, it must be an invisible positive 1 sitting out here. So I can either leave it like this or write in a positive 1. Either way is fine. But this is our final equation of this absolute value. Number 8, however, has shading, it has dashed line, it has all kinds of things that we need to account for. So let's see, what would we build for this one? Well, we still have y, and we have shading below, so y must be less than. We have dashed line, so y is less than but not equal to, so I don't put a little equal sign here, I just say less than. Let's continue to build our skeleton. We know it's less than, it's a v, so it's less than the absolute value of some kind of absolute value of x. So let's find our starting point here. It looks like it's at negative 3, comma, 1, 2, 3, 4, positive 4. Again, I highly recommend you write that here before you come down here. So if that's the starting point, that means in here I write a plus 3, and out here I write a plus 4. Now, what is the quote-unquote slope, or the a value that goes out here? Let's pull that off the graph. To get from here to the next point looks like it's here, and then there's another one here. So let's see what the constant ratio is. It looks like we go down 2 over 1, down 2 over 1. So it looks like I have a down 2 over 1 scenario, a negative 2 over 1 scenario. And it's upside down. So I knew it was going to be negative, but I need to fill in a negative 2 here for that slope. And so that's your final. Y is less than, but not equal to, negative 2 times the absolute value of x plus 3, and then a plus 4 on the outside. All right? Go ahead and try your independent practice.